You haven't picked up your project, part 1, pick it up at the end of the class. So there is going to be a midterm, and that's going to be either on the Thursday of the first week after the spring break, or the Thursday after the second week after the spring break. Okay, I'll let you know, but so you should be prepared for one of those Thursdays. If there is going to be an in-class exam for the final, it would be on the day that is in the catalog. I think it's it's May 11th or something. I put it up on the web. Okay, that's the final exam for the course. The project 1, part 1 statistics will be sent to you by the TA. And as I said in our mail sent to the class, if those of you who do not really want to work on project 1 and want to get going with project 2 with the help from project 1 code, you should let us know if you need the code for project part 1, because these are cascaded projects. So you cannot do project part 2 if you don't have the part 1 code. My hope is if you haven't completed part 1 by the deadline, you would still complete it by the time of part 2 deadline. That way you'll at least get some partial credit, and plus of course you'll learn how to do this. But if you prefer to just ignore project part 1 and go with part 2 instead, then you have to talk to us, and we'll give you, just on a case-by-case basis, we'll give you the code for the part 1 so that you can go to part 2. Okay. Any questions? Yes? Yeah, I mentioned that it's going to be either in the Thursday in the first week after the spring break.
Kind of questions?
What?
Kind of questions? Problems or?
I will probably send you a specimen midterm, but they'll basically be much shorter versions of the homework problems. Okay, I will send you probably a previous midterm just to give you an idea. Okay. Questions? Other questions? Okay, so I am going to continue the discussion of the social networks, which we were in the middle of last class when we left. So what we were doing last class was Kevin Bacon game and Erdo's numbers, all of which essentially seem to suggest that the human networks have small world phenomena associated with them. That means the length of the path between any two members in this network seems to be sort of logarithmic in the size of the network. Okay. Another way of thinking about it is you also talk about diameter of a network. A diameter of a network is the longest path between any two nodes. Okay. Longest geodesic path between any two nodes. Okay. And so if the diameter is not of size n, where n is the number of nodes in the network, but rather it is of log n size, then you are sort of surprised, because there is basically seems to be just a few hops and skips between you and anybody else in the network. Okay. So of course this came into popular imagination with Milgram's experiment, which sort of mostly for historical reasons. I should mention that Stanley Milgram did this experiment back in 1967, I think, where what he did was he supposedly took a bunch of random people from Nebraska and asked them to send a letter to a stockbroker in Boston, not by posting it and not by giving the address of the stockbroker, but rather by saying, guess which of the people you know might know that guy, and then give it to them, and then they will do this until it reaches the stockbroker. Okay, so presumably this is a way of seeing whether there are short paths between people in the social network. Okay, up front, supposedly these guys didn't know anything at all about this last person, who's going to get the mails. And what he found, here is the packaging that he put in. what he found was among the letters that found the target, the average number of links was 6. That means people gave 6 people were in the link that connected anybody to the stockbroker in the end. And that's where this notion of 6 degrees of separation, which sort of became part of the popular imagination, came up. Okay, there are actually a huge number of problems with Milgram's experiment, and in fact, the way he conducted that experiment basically is flawed, and it makes no sense that his results were actually kind of right. In the sense, in fact, human networks do have the small world phenomena, but his experiment itself, because it became famous enough, people then looked into the experiment and found all sorts of problems with it. Here are some of the problems. One is that, in fact, he was trying to send this to somebody in Boston. Okay, that's what the advertisement was. You'd think Nebraska, you wouldn't think there are stockbrokers in Nebraska. You think people who are sort of farming. And these people in Nebraska are able to reach some stockbroker in Boston. That's very surprising. Except, in fact, most of the test subjects that he was dealing with were themselves stockbrokers. They happened to be in Nebraska. Okay, so he found a few stockbrokers in Nebraska and gave them this. So they probably are likely to know how to reach the goal stockbroker. He did not obviously mention this at the time when he published this study. In fact, here's you can always cheat in your life, but just hope that you won't become famous. Okay, if you do become famous based on your cheating experiment, then people will find out what happened. And ultimately, the only way you can cheat and not be detected is you did work that nobody cared about. So nobody really ever wanted to replicate. Okay, that's a reasonable thing to aim for. But if you want to do things that will change the world, make sure that be completely aware that people are going to just look at every piece that you have ever done. So anyway, this is, in fact, large fraction of his test subjects, supposedly they are from Nebraska, but they are actually in Boston, as was the gold stockbroker. And then, furthermore, when it looked like a large number of letters reached and the average length was 6, but actually only 20% of the letters reached the stockbroker over a 6-month period or something. So really the amount of, so this was an experiment that he set up hoping for the result that he got. Okay, and as soon as he started seeing some kind of a result that supported it, he went ahead and wrote papers on this and he became very famous on this. And in fact, I think supposedly there was this movie, 6 Degrees of Separation, which kind of made it into popular culture even more. But the interesting thing is, even though the experiment is flawed, and in fact there have been attempts at replicating Milgram's experiments in the current day and age, where you essentially send it by email to somebody you know and ask them to send it by email to this last person whose email address you don't know. And they have actually confirmed the small world nature of our networks, the human networks. Okay, so even though Milgram's experiment was flawed in the final analysis, his results were right. Okay, so human networks actually seem to be having small world phenomena. So the question then is, can we explain this? Is this something particularly crazy about human networks, or is this something that can be mathematically explained? And for that, we will start looking at random graphs. Yes, sir.
If he came up with the right answer, then why in his case did only 20%? Did it only work 20% of the time? If it really is.
No, he was taking the average over only the letters that actually did reach. Imagine the following thing. You gave it to 100 people, okay? You gave these letters to 100 people, and only one finally reached the stockbroker in 6 months' time. And the one that did reached with 6 links. Would you then be happy with the hypothesis that says, everybody is connected to everybody in 6 steps? That would be a much harder thing to believe. So he essentially did not make clear, apparently, how many letters did reach.
So he didn't say anything about the 80%?
No. Okay. But again, look, I think we get to yell at him only because he became famous. Okay, so it's reasonable. It's like you get to yell at Newton for his crazy things that he did to Leibniz about calculus only because he became famous and he got every possible credit for inventing calculus, but it's also understood that he, did a lot of bad things to Leibniz. Okay, go ahead.
Well, it kind of makes sense to drop the letter star 100% because there could be 1 degree of separation, and that one person may just be too lazy to reassemble letter.
I understand. So again, what I'm saying is, all I'm saying is, if only 1% reached, you would not have been writing this paper. I would say 20% is reasonably close to 1% than it is to 100%. Okay. So anyway, so let's look at the random graphs. So here are random graphs, and how do you make random graphs, first of all? So when I talk about random graphs, what do I mean? Okay, a random graph actually was studied by, the properties of random graphs were originally studied by Erdos, the same guy we were talking about a while back, last class, Erdos, number Erdos, and Rayleigh. Basically, they wrote this work in 1959 that we'll be talking about today. But first, understand what a random graph is. If you have n nodes, you decide a probability P with which any pair of nodes will have a link between them. Okay, so presumably all you need is, the 2 parameters you need is the network size n, okay, and the probability P that any random pair of nodes will have a link between them. So all you assume is you have a coin which comes up heads with P probability and tails with 1 minus P probability. Okay, so then you have n choose 2 combinations of nodes in the n node network, right? And n choose 2 pairs of nodes, in the n node network. So for each pair you pick, you toss the coin. If it comes heads, you'll put a link. Otherwise, you don't put a link. Simple enough? Okay, this is a generative model. I'm generating the random network by doing very simple things locally. So individual nodes will look around all the nodes in the network and make a node, a link between them and this other guy with probability P, with each pair with probability. Now, not surprisingly, if you are one node, you can at most have n-1 links, right? Because you are one of n nodes, you can have a link to everybody else, so you have n-1 links. So of the order of n links, okay? And then the expected number of links you will have is P times n-1. This is the expected degree of a node. We'll assume that the links are non-direct in the random graphs. Okay? So the expected degree of a node, or the average degree of the node, k, is P times n. Okay? So here are how random graphs might look. For example, P equal to 0, k equal to 0. If P is 0, of course k will be 0, right? And so it will be all n nodes. None of them are connected to anybody. So it's just a disconnected components. If you have P equal to 1, then k would be about half n square, because k would be n choose 2 times 1, which is n choose 2. And n choose 2 is about n square, right? So that would be a complete graph. You would connect everybody to everybody. Okay? In the middle, basically, are any other probabilities. For example, for probability 0.09, the number of so k became 1 here because how many nodes do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 0.09 would be close to 1. Okay? So that's your random graph that you got. Now notice that if I were to generate one more random graph with these same parameters, would I exactly get the same thing? Of course not, because it depends on how the coin toss worked. In fact, the only 2 networks that will always be the same are this and this, because one is P equal to 0, another is P equal to 1. Those are deterministic cases. Everything in between would essentially be a different configuration every time. But the density, the average degree of links is about P times n. That's the case. Okay, so those are your these are random graphs for different values of P. Now the question is, what can we say about these networks? What can we say about these networks? The reason we are discussing these, of course, is we cannot. It's not easy to provide results about actual human networks. So let's assume that human networks are somehow related to random networks, and then see what the properties are for the random networks. Okay. So, if you are actually trying to look at the properties of these three networks, what kind of properties would you be interested in? You would be interested in at least these three properties. One is the size of the largest connected cluster in the network. Okay, which is what is connected cluster means. In that connected component, every node is connected to everything with a finite length path. Okay. The other you're going to be interested in is the diameter, which is what is the longest geodesic path between any two nodes in that largest connected cluster. Okay. Now the finally average path length. This is the diameter. This is the worst case. Average path length. What is the average of all the average of all pairs of nodes? The geodesic path length. Okay. Now, if you are looking at these cases, this and this are easy enough. In this particular case, what do you think would be the largest connected cluster size? 1. Because each node is a cluster by itself. Okay. So 1 here for this. What's the diameter? Diameter is 0 because they basically, you are within each cluster is just one node. And average path length is also 0 on this side. Okay. So you have 1, 0, 0 here. Now let's look at this side. If you look at this side, the size of the largest connected component is the entire graph. Okay, it's a complete graph. Complete graph means everything is connected to everything. So the size of the largest connected graph, in fact, is 12. Okay. Now what is the diameter? Diameter, because it's a completely connected graph, every pair of nodes is exactly one distance away from each other. So the diameter actually is 1. Since everybody is 1, average is also 1. Every pair has distance 1, the average distance is also 1. So here is an interesting thing. The size of the largest component here is 1, it is 12 here, the diameter of the largest component is 0 here, which is really small, and it's 1, quite small. Now, if you look at this and this as the extremes, what could be the largest value for the diameter? Of all the random networks that you can draw over n nodes, what would be the largest diameter? N minus 1. Right? Because you put everybody in a line. If you put everybody in a line, then you will get essentially of the order of n as the diameter. Compared to order of n, if n is basically a million, it doesn't really matter. These numbers don't depend upon, especially the diameter number doesn't depend upon how many nodes are present in the network. You could have a million nodes in this network and this guy's diameter will still be 1. And the average path length will still be 1. And you can have a million nodes in this network. For these parameters, its diameter would be 0, average path length is 0. So in both extremes, the diameters are small. Okay, if I take the Milgram's kind of a view, that is, I'll only consider the path lengths over connected clusters. I'll only consider path lengths over connected clusters because if you are unconnected, then you have 1 infinity there, and if you take even 1 infinity and add a whole bunch of finite numbers and divide it by a finite number, it gets to an infinity. Right? So normally we would look at path lengths in terms of the connected clusters. So in fact, these two extremes seem to be pretty good small world networks. Right? The diameters are less than log n size. Okay. Now what happens in the middle? For example, these are not as easy to actually see directly, but here is p equal to 0.045, which gets you a k of 0.5, which means of the 12 nodes, you will get about half probability half that any pair will have a link between them. So half the pairs have links, half the pairs don't have links. Okay? I'm sorry, no. Sorry. The probability that a pair has a link is 0.045. Okay? K equal to 0.5 means if you were to generate the graph using this probability for link, then the effective degree of any node would be 0.5. Because many nodes will have 0 degree, some nodes will have degree 1, and then the total will be about 0.5. That's what I mean. K equal to 0.5. In this case, if you look at this particular graph, okay, it's a small enough graph, you can see that the largest connected component is 5. right? 1, 2, 3, 4, 5. That's a connected component. Okay, and then the diameter in this is 4. 1, 2, 3, 4. Okay, and then the average you can see for over all those pairs. You can compute the average. It will be 2.
So how did you come with K?
What?
How did you come up with K?
K is 3 times n. K is the expected degree. K is the expected degree. Okay, the only two parameters are P and n, and K is just a derived parameter. It's just the expected degree. Okay, now for point, so suddenly, interestingly, largest component has become 5 here. You know, component size used to be 1 here, it used to be 12 here, it became 5, and that's not surprising. More surprisingly, the diameter increased to 4. Okay, now 0.09 K will become 1. That's the expected degree is 1. Okay, and there in this particular graph, you can again show for yourself that the largest component has 11 nodes in it, because this is the only node that's not connected to anybody. Okay, and then there is the diameter is 7. The largest geodesic path, longest geodesic path is 7. You can look it up and see. And then the average is 4. Now, what?
What is geodesic?
Geodesic means the shortest distance. Okay, because I mean I can go from node 1 to node 2 by repeatedly going to node 3, node 4. You are not allowed to do that. Okay. Okay, so what's interesting here is the following. We see a pattern emerging. The pattern seems to be that if you were to draw K, if you were to draw, you know, x-axis K, okay, and on the y-axis diameter is low for low values of K, it's low again for high values of K. Agreed? Okay, it's low here and it's low again there. Okay, so, but diameter is increasing in between. So I would think if there's two, you know, if you have a function which ends in two sides on low and it is increasing in the middle, what would you think? You should not be surprised that if the function is like that. You should not be surprised. Right? Okay? So diameter is in this case. And then, so what you will be surprised, however, what you should be surprised, however, is if I were to tell you that the diameter would be like that. Because that curve also will be low on one side, low on the other side, and it increases in the middle, but it seems to be increasing in a very narrow region. Okay, if you want to get a paper on this, you better have surprising results. Okay, if in fact Erosion and you showed that of course for the large K, diameter is low, for the small K, diameter is low, for in between K, sort of diameter increases and then again falls down. Okay, if you say that, then basically, so what happens on this side is that everybody is living in their own little worlds because they are not connected to anybody. In a little world, diameter cannot be too large. Okay, if in fact in this particular case, each world is just one node and thus the diameter can only be 0. If, you know, for a slightly larger K value, you might have, you know, 2 node clusters. And how big would be the diameter in any connected cluster? 2, I mean, actually 1. Okay, so you should not be surprised that the diameter is low here, it's low here, but it would be interesting if in fact diameter goes like this, and surprisingly enough, that's exactly what happens. Okay, in fact you can show this, you can show, and you know, I would ask you to read this paper. It's a very nice paper. It's not all that hard to read if you have some background in elementary probability theory. Okay, that in fact when K equal to 1.0 is the phase transition point. Now why do I say phase transition? Because the last time you heard, if you didn't do AI courses, the last time you heard phase transition was where? Thermodynamics, or if you just ever boiled water to make coffee, right? When you boil water, you have a phase transition. The reason it's called phase transition is what? Water is always trying to become vapor. It's always trying to become vapor, even at room temperature. The interesting thing at 100 degrees centigrade is all the water wants to immediately become vapor. So in fact, everything that's going on in water is just becoming vapor. So in fact, the temperature gets clamped until all water becomes vapor. That's why it's phase transition. And you get Nobel Prizes for explaining why phase transitions occur in physics. Steven Weinberg, for example, got Nobel Prize for phase transition research. Now, here, interestingly, you actually have a phase transition around a sharp threshold around k equal to 1. Okay? Around k equal to 1 is a sharp transition. And what's interesting basically is k less than 1, as I said, the world has small isolated clusters. Nobody talks to anybody. It's just small, it's like cavemen, alright, cave people. And if the cave is not too large, so you cannot have very large diameter. Okay? And then, so obviously small diameters and short path lengths for k much less than 1. K much greater than 1, it's almost all nodes are connected. Okay? And diameter shrinks because everybody is connected to everybody multiple different ways, so the shortest path would just be one link. And path length shortened. Diameter shrinks and the path length shortened. Around k equal to 1 is where a giant component occurs, which is almost sort of, in the worst case, it will be a chain. That would be the worst possible case for a network. A chain means that the diameter now is going to be n. Okay? What's interesting, of course, is that exactly around 1, the numbers change significantly. That's why it's a phase transition. Now, if I look at this, it is actually a very interesting point. In fact, the fact that there are phase transitions in computational problems is quite interesting. Okay, those of you who have done AI courses might know that, for example, if you generate random SAT problems, then there is a threshold. If you consider the random SAT problems, random 3 SAT problems, and consider number of clauses by number of variables as the parameter, then the difficulty of solving the problem peaks in a very narrow region where this guy happens to have magic number 4.3. Nobody actually knows exactly what that magic number is. In this case, we know the magic number, it is 1. The phase transition occurs at 1. Okay? So it's interesting in itself, actually. I think several of you should be interested in figuring out how you prove sharp threshold phenomena. What is more interesting to you is what does this tell you about human networks? So, k equal to 1 seems to be the sharp threshold phenomenon, is the sharp threshold, below which and above which it's small world. Agreed? Only k equal to 1 is a bad case. K not equal to 1 is a less or more, you would be small world. If you are doing random networks, if human networks are random networks, what would be k?
700,000.
Are there any sociopaths here who have no friends? Most of us will at least have one friend, maybe more than one friend. Okay? So if the average number of people you know is more than 1, then if your social network is a random network, then your k is greater than 1. The moment it's even slightly greater than 1, you are in a small world network. Okay? So, the interesting point about this picture is, where are the human social networks in this graph? On this side. Okay? I mean, for cave people also, if you go into the Google opt-out village of some sort, then essentially again, you would have no friends other than just yourself, and again you will be in a small world network consisting of just yourself. Okay, but very few are in that side. But most of us are in this side. Most of us have more than one friend, not less than one friend. Okay, so on the average our friends, or the average our social connections are more than 1, which is a very normal observation, actually has a pretty nice theoretical implication that you should be surprised that you are in a small world network. Yes, question?
I didn't understand the graph. Is it the average diameter?
What?
Is the graph the average diameter for that k?
No.
Basically
Average diameter. Average diameter. Because the point he's making is, for each k value, you would essentially generate many random networks for that k value, compute their diameter in each case, and take the average. That's what this is. Okay, any other questions on this? Yes.
Just, if you go 3 slides back, there's one slide where you said a completely connected graph is k equals 1 half n squared, then it changes to k equals n. Now,
No, k equal, no, actually it's wrong. It's half n squared is wrong.
Yeah.
Because k should be n minus 1. Yeah, this should be changed to n minus 1. I will change it when I go. Okay? Again, k is, it's not a magic number, it's just the expected degree. And if your probability that you will be connected to any other node is 1, then you can at most be connected to n minus 1 nodes. That's it. Exactly n minus 1 nodes. Not n. Okay. So, this is good. We seem to be done. We have explained, I say, that you should not be surprised about Kevin Bacon game. You should not be surprised about the Erdos numbers, and you should not be surprised also about Milgram experiment. Because after all, random networks have small world phenomena for the normal values of k. Yes, sir?
My understanding is when Milgram was doing his experiments, it was local routing. So you can't just look at the graphs, you should suggest routing.
No, you are talking about a very different issue. All I am saying here is, I'm looking at the diameter of the network as an oracle who has access to the entire network. Okay? If the diameter of the network is already 1, okay, then even local routing cannot take more than 1 step to reach the destination. The point you are making is navigation on a social network. We will get to that. In fact, navigation over a social network is a very interesting exercise for humans who tend to navigate their social networks locally. Okay? At least, especially before before the advent of web, when social networks are available on the Facebook or something, to actually figure out if you know somebody who is doing this kind of work, you really have to look at all your friends and their friends and their friends, ask bunches of questions until you find this person. If you have the entire graph in front of you, which you normally never have because your friends don't tell you who their friends are, okay, you will not be able to find this path. So navigating a small world efficiently is a very interesting question. We will come back to this later. Okay, but on the web, it actually almost doesn't matter because Facebook doesn't navigate small world with local decisions. It knows everybody's information. So it can just magically suggest to you that this is the person who is 4 links away from you who knows this subject. That's essentially what Aardvark will do. Aardvark that I was talking about last time. They are not actually going to do this inefficient thing of asking your friends and their friends, etc. locally. They just do global navigation. Okay, but if you are doing physical, if you in fact don't have the global database, then you will have to do local navigation. And there's an issue of when is navigation efficient. We'll get to that. But none of that affects whatever I said here. And I sort of set you up to say, I have proved to you that, you shouldn't be surprised that human networks are small world. Yes, sir.
This is assuming we say that social networks are random.
Exactly. So the big if. So basically this is what I just said, that if connections between people can be modeled as a random graph, then because the average person easily knows more than one person, that means k is greater than 1, and there is a sharp threshold at k equal to 1, okay? So it's like saying 101 degrees. Can you get me room temperature, can you get me at the normal pressure, can you get me 102 degrees water? Impossible. Because at 100 degrees it all became vapor. Okay, you need to have a steam cooker to actually increase the pressure so that it will be at 102 degrees. Okay, so basically, since k is greater than 1, you know for sure that in these random networks would be small world. Okay, so we live in a small world where, of course, within a few links we are able to we are connected to everyone else in the world. Okay, that's kind of nice. And in fact, Erdos and Renyi showed that the length, essentially the average path length between the connected nodes is log n by log k. Okay, so it is our logarithm of n, right? So that's basically what we hoped would be a small world network, and that's exactly what it is. So now it looks almost as if it is exactly what we wanted, except there's a big if, which gets us to interesting discussion. The big if is, are indeed human networks random? When was the last time you made a friendship in this class by saying, oh, okay, I have a coin now. I'm looking at this guy. Heads, so I'll be friends with him. Okay, tails, no, I won't be friends with you. How many times do you do that? Okay, basically, human social networks don't seem to be random. At least it doesn't look as if, by introspection, you don't seem to think that they're random. Now, introspection has already been called worst form of psychology. And introspection also is worst form of mathematics, right? So just because you think it's not going to happen doesn't mean it doesn't happen. So you really need some kind of an evidence, okay? What evidence can I have? Let's look at that. So let's actually talk about large-scale social network and see if in fact they were, if suppose you had access to the Facebook social network, okay? What questions would you ask to check whether or not it's a random network? Do you understand what I'm saying? So in fact, if you think that a network is random, what would be a hypothesis that will be valid for that network? If it is not valid for the Facebook social network, then you will say, looks like it's not a random network. Okay? Now, in fact, one interesting question is the degree distribution. We said basically that the average degree is k, which is p times n. That's the expected degree. Okay, so suppose I tell you that the average mark in this class is 65, that only tells you a piece of the information. It doesn't tell you how the marks are distributed. Normally to give the distribution, I'll also have to give you some sort of a histogram saying where are the marks. And there may always be some real bad people who are getting 150 out of 100. And they're pulling the curve down or curve up, depending on what you want to see. Okay, so the average may still be 65. It's only because of this outlier guy. And if you remove them, the average will be a happy 20, and everybody will get an A+. Okay, so the point I'm trying to make is average is just one piece. What you really need is distribution of the degrees. Distribution of the degrees over nodes. Okay, so let's ask ourselves, what is the probability distribution over the node degree in a random network? Okay, so here's my question. What's the probability that a random node, random vertex V, has k edges from it? That means it has degree k. Right? What that means is it should be equal to k. This is, by the way, this question is like saying, if I toss a coin 100 times, what is the probability that I will get 25 heads? And the thing that you remember from your old combinator rigs is that 25 heads can come all in the beginning, all in the end, somewhere in between. So all you care about is how many different ways can you get 25 heads over 100 tosses. You need the combination. Okay, so if I need to have exactly k degree for a node, then I need to take k friends from n-1 people, n-1 vertices. So that is n-1 choose k. And then with all the guys that I chose, the probability for, I would have an edge with them. So that will be p times p times p times p. They're all independent, right? I'm saying that random networks are independent. So whether or not I'm going to be a friend with him is independent of whether or not I'm going to be a friend with you. Because when I'm looking at you, I toss my coin once. When I looked at him, I toss my coin again, separately. So they're independent events. Okay? So this is n-1 choose k, p power k, 1 minus p power n-1 minus k. This is important too. For example, it's not just enough to say that there are 25 times the heads came. The rest of the 75 times heads should not come, which means tails should come. That's how you get exactly 25 heads. Okay? Similarly, you have, this is the case in which you will have exactly k edges from a node. So this is your distribution. This is the probability distribution. Okay? Now, if n tends to infinity, this can be shown to take essentially the form of what's called the Poisson distribution. Okay? A Poisson distribution is, log, the bell curve, which is the distribution over continuous variables. Okay? This is the distribution over discrete variables. right? Because degree can only be 1 or 2 or 3 or 4. It can't be 1.75. Okay, so this is a discrete distribution, and basically this is the standard form for the Poisson distribution. It's lambda power k e power minus lambda by k factorial. Yes?
Was this done with social networks like Facebook, or was
No,
this
no,
done
no, I'm
with-
just, no, this, what I'm doing is this. Suppose I have a Facebook social network, okay? What questions can I ask that network to see whether or not it could have been a randomly generated network?
Right, I guess
Okay.
I'm jumping ahead because I'm asking more, because Facebook in a lot of ways is random, just because a lot of people just add friends.
Yeah, so I think basically the word random here, what we'll see is when we say random network, you know, it's a particular type of random. In fact, it is uniform random. So that means the probability that I will have an edge with him, or the edge with you, or the edge with him, are all uniformly p. Okay? What you're thinking in your mind essentially is it may be a non-uniform. We'll get to that in a second. Okay? If in fact the probability that you will have an edge with somebody is uniformly p, then this would be the way your degree would be distributed in the network. Okay? So obviously the probability that you have a very low degree versus very high degree would be dependent on what this expression evaluates to. And for different values of lambda, so for example for Poisson distribution, for a Poisson distribution, both the mean and the variance are lambda. That's the interesting part. Okay? In a normal distribution, the mean is mu and the variance is sigma. Okay? So there are two parameters to specify normal distribution. For Poisson distribution, you just need one parameter. Essentially, that's lambda. So if here is how the distribution looks graphically for different values of lambda. Okay? Here is lambda equal to 1. Here is lambda equal to 4. Here is lambda equal to 10. Sort of, if you look at these parts of Poisson distribution, it is sort of like bell curve. As the lambda increases, the bell becomes more and more flat. Normally, you can change the mean as well as the variance independently for a normal distribution. In a Poisson, that's not possible. Okay, but this is how you expect the degree distribution to be. Okay, so what I need to do is look at the Facebook social network, look at the degree distribution of all the nodes, find a histogram, and see if that histogram looks like this. If the histogram looks like this, then it could have been generated by a random, uniform random generation. If it's very different from this, then no, it couldn't have been. Yes?
But in the case of k equals 1, does that look like powerlaw?
We'll talk about that in a second. Okay? Keep that in your mind, but you can answer that later. Okay, so this is where we are. So I'm just going to look at Facebook and then look at the degree distribution and then just draw, find a histogram for it and see if it kind of looks like this. Okay? Here actually are the degree distributions on real networks. A is the World Wide Web hyperlink distribution. Okay? B is the co-starring in movie distribution. C is the co-authorship of physicists. D is the co-authorship of neuroscientists. These are all real networks. More real than the ones that I just read by tossing points. And I chose, for weird reasons that you will get, I could have drawn a nice little, histogram, right? Instead, I chose the degree distribution. I represented the degree distribution in essentially a log-log space. So it's a double log curve. Okay? Now, if it's a double log curve, one of the interesting things I'm seeing is in the log-log space, the degree distribution is becoming a straight line. Okay? If you remember anything about mathematics, you'll realize that these are exponential curves. If you remember what's happening here, this is e power minus lambda. Right? Okay? Lambda power k e power minus lambda. So if you look at the log-log space for this, you couldn't have gotten straight lines. In fact, to get straight lines, you really need a different kind of distribution. You need a distribution that is sort of 1 by, it's basically proportional to the degree k power minus r. No, the degree k is being exponentiated to r, some number r, okay, r greater than 1, and so k power minus r means it's 1 by k power r. If you take logarithm for that, and if you plot that in the double log curve, in the double log space, you will basically get a line, and the line would be the r value. The line would be r value. So this basically is a convoluted way of saying that indeed I looked at real networks and they don't seem to be at all like random networks. You knew this already because you did not seem to be making your friends randomly. Now this is a more large scale proof, large scale empirical demonstration that in fact the degree distributions in the real networks are not Poisson, which is what you would get if it's a uniform random network. Okay? But instead of Poisson, you seem to be getting what's called 1 by k power r kind of a distribution. Okay, notice that both Poisson and k power r, 1 by k power r, have the property that as the degree becomes really large, the probability would be really small. Right? Okay, but the interesting question is how fast does the probability become really small? So this was a question that this guy was asking previously. So in fact, okay, if you look at this in not in log space but in normal, without logarithmic, in the normal space, the distribution for power laws looks like that. Okay, distribution for power laws looks like that, whereas distribution in the normal space for Poisson distribution looks like this. In fact, here this is also actually a, for a real random network of a large size, these are the actual probabilities, and this is what would be theoretically predicted, and you notice that for a large random network, in fact, the degrees would be that way. Whereas, the power law would be like this. Okay, now here is an interesting question. This looks, as that guy was pointing out, suspiciously like this. Right? This 2 is falling. It looks like a sort of a little power law. That's why he was thinking. Because over a period of time, power laws have become part of popular vocabulary. So everybody thinks that they're seeing power laws. But one of my hopes in the rest of this class as well as next class is to make sure that your intuitions about power laws are correct. Okay, just because something becomes rarer as k value increases doesn't mean that it's a power law. In fact, ask yourself the following thing. Between this and this, for a large value of k equal to 10,000, how does the probability according to this compare to probability according to this? Which would be larger? Power law would be significantly larger. You're a computer scientist. Okay? This is k power r. This is a polynomial. The other guy is an exponent. In this case, k is in the base, r is a fixed number. As k increases, you are increasing polynomially. And in fact, in this case, you are reducing polynomially. Whereas here, the k is in the exponent. Lambda power k. So exponents will do everything more. Right? So in this particular case, it falls down much more. Okay? So the first thing I want you to understand is in power law distributions, rare is not so rare. Okay, many of you, I don't quite know which any specific people here actually have this misintuition, but most common misintuition about power law distributions, which these are, is that, oh my God, the rare things, that somehow you focus on this side and say rare things become significantly less probable. Okay, but the point about this is the tail. The tail is, how much of the probability mass is focused, is concentrated around the mean, and how much is concentrated away from the mean. Okay, And so what would you say in normal distribution? I would say that the probability mass is generally more concentrated around the mean than in power law distributions. Power laws are also called long tail distributions. Long tail means that the tail doesn't die. Okay? If you do not, in fact, for example, many things have these long tail distributions. For example, we'll see that not only social networks, the Zipfian distribution is a power law. It's a 1 over k, that's it, where r equal to 1. Okay, so power law distributions occur in practice a lot of times, and the point that we want to understand is, one other thing is people's interest in buying music. Okay, presumably, obviously, whatever is in the top 10 in the bestseller list is what most people probably would buy. You know, if Britney Spears in the bestseller list, you will buy that Britney Spears. Now, you are a new, salesperson, who are interested in getting into retail music business. So you know that people will keep buying these top 10 things anyway. The real question is, do you think there will be enough people who would be buying, for example, classical music recorded by Slovenian orchestra? That's obviously very far from the mean. It's not very popular. The question is, would anybody buy it? Okay? In the old days, when you had brick and mortar stores, they were hoping, essentially, they were forced to hope that the tail is short. So what do you mean you don't like Britney Spears? We'll put 10 different albums of Britney Spears. I'm sure you like one of them at least. And what do you mean you want to learn, listen to some Iranian classical music or Indian classical music? Go somewhere else. Okay? The big change is, in fact, to realize that the musical tastes actually don't fall exponentially. It's not that the interest in Iranian classical music is exponentially lower than interest in Britney Spears, but that interest in Iranian classical music is only polynomially lower than interest in Britney Spears. Which now means that if you can somehow drive down the cost of mailing and selling the stuff to people, which you can do by having an Amazon or something where they'll have every damn thing in some one central warehouse, and then now I want like yesterday I decided to buy West Wing season 2 DVD set. Okay, what is the chance that if most of you probably don't even know what West Wing is, but those of you who do, what's the chance that if I walk down to an actual store, I will get West Wing season 2 DVD set? And what's the chance that they'll sell it to me for any money that I can afford? I looked at Amazon, it's available for $23. And it's not that like there's a big rush to buy it, but there are never vanishingly small number of people. There's a long enough tail that they will still make money selling the West Wing cassettes. So I bought one. Okay, you should tell this to my son because this is going to be a surprise for him after spring break. But anyway, so the point that I want you to understand is long tail is important. So if you were to put degree distribution on the web, let's say incoming node distribution on the web. Normally web has a directed degree distribution, directed edges. So you should be actually talking about distribution of incoming links as well as distribution of outgoing links. The interesting thing is both incoming and outgoing links have power law distribution. Okay, just a second. So my question is the following. If this was the incoming degree distribution for the websites, where is the Google and Yahoo sites in this network? Where is the Google and Yahoo sites in this network? What? It's here. If you thought it's here, because Google is big, this is big, it must be that's where Google is, then you're wrong. This is where your degree distribution is. Most of us have incoming degree of 0 or 1. Nobody else other than our wives and husbands point to us. Okay? So this is the unwashed masses. We have most number of them with 1 or 2 in degree. This is where maybe Yahoo will be living. This is where Google is living. Do you understand what I'm saying? So, here is my question. If the world was uniform distributed random networks, would there have been more or less probability of sites like Google and Yahoo existing?
Yes, sir.
Much less. Much less. Okay? So that gets me, so that's basically in power law distributions, rare events are not so rare. Okay? As in exponential distributions. So this is the tale of tales. Okay? So you may want to remember this. So I'm showing you 3 distributions here. This is a uniform distribution. You can think of this as distributions over, let's say, degree. So this is a uniform distribution where somehow the degree is only between A and B. And, and between A and B, the degree distribution is uniform, outside of it is 0. This is Poisson or something like a normal distribution. This one is a power law distribution on the same thing. They all have tails. The interesting thing is this has 0 tail. It has no tail. This one has a very short tail. This has a long tail. Okay? So uniform distribution, no tail. Exponential distribution, fast vanishing tail, that means short tail. Power law distribution, long tail. Now here's an interesting question. How many of you have heard of this idea of Six Sigma kids? Like for example, why do we decide, so here is another different question. So I have to make a decision when you have your final grades, right? I look at, cumulative grades, I make a histogram. Histogram is histogram. But then I need to have a model as to how this histogram is generated. Was this am I supposed to fit to the histogram a exponential distribution, which is like a normal distribution, or a power law distribution? Of course, all your life you've been told that you are supposed to fit a normal distribution. Okay? And the normal distribution essentially has this nice little property that you draw the graph like this, and then this is your mu, this is your sigma, this is 1 sigma, this is 2 sigma, blah blah blah, this is 6 sigma. 6 sigma kids. These are the 6 sigma kids. Okay? We talk about 6 sigma kids in any field. Those are like off the scales. It's so rare to have a 6 sigma kid, or 6 sigma musician, or a 6 sigma, anything. And in fact, that came from the exponential distributions, because we assume that most distributions are normal. If in fact I tell you that the underlying distribution that generated the class cumulative marks was power law, then 6 sigma kid is not that special after all. Do you understand what I'm saying? It's not special. So Google is not that special in a power law world. It would be like really, really special in a uniform random world. Because it's the probability that something like Google can exist in a uniform random world is significantly lower, exponentially lower than that it exists in a power law world. Okay? Any questions on this one? Okay, so basically I have made connected points here. We started by saying, if in fact you have a random network, its degree distribution will be Poisson, okay? And if, in which case, in log space, it won't be a straight line. And yet, most real-world networks seem to have straight line in the log space, which corresponds to the power law distribution, which is basically 1 over k power r, where r is the exponent, and it's changing. The bigger the r, the faster the power law falls. Okay. So now, and I also pointed out some common misconceptions about what is more surprising. Long tail in the power law distribution means it has a much longer tail than in the normal exponential distributions, such as normal distribution. Okay, we looked at all that, and in fact, as I said, for many things, R is sort of between. It has to be. For most of these networks here, I think actually the R was shown.
What is R?
R is 1 by k power r. It's a constant. It's a constant. It's a slope of this one. It's the slope of
So
this
you're
line.
saying it's decided by the empirical data rather than the actual.
Yes.
It's not something.
Okay, so now the interesting question is, one of the interesting questions is we went from a generative model for uniform random networks to its emergent degree distribution and then said, no, that's not what you are actually finding in the real world. You are finding this in the real world, which brings up the question, what should people be doing locally such that you can get something like this? That's the generative model for power law distribution. We'll talk about that in a minute. Okay, that's also kind of related to a question you talked about. Okay. So and then we talked about the tail of tails. Now we get to talk about random versus real networks. If a random network would look like this, this is not example, it's just an example of random network. Here is how a power law network would look. It's also called a scale-free network. We'll see why it's called scale-free, mathematical reason in a minute. Okay? But you'll notice that there tend to be more nodes in this, which kind of authorities and hubs in this than here. So the point is, authorities, hubs computation and page rank computation would be basically useless if in fact the web was generated by uniform random networks, because maybe a couple of people will have a high page rank and everybody else in the world will just have 0 page rank or 1 page rank. Okay, the long tail means there are enough people who do have, even though you are not one of those successful people, there are enough people who have page rank 4, page rank 5, etc. Okay. Now, so random network models introduced, this is the generative model for this, and if you use the generative model, you get this. Real networks actually tend to have a relatively few nodes of high connectivity, and these networks, if you do this degree distribution in the log-log space, you'll get a straight line, and those correspond to the power law distributions. So let's talk about power law distribution. Okay, if you have a probability distribution, what do you care about a probability distribution? You care about its movements. First order movement, which is mean, second order movement, which is variance, and so on. Okay, now here is the interesting thing. Suppose r equal to 1. This would be 1 by k power r equal to 1. That means it's 1 by k. What's the area under a curve which is 1 by x? Take up. You did this in calculus. 1 by x. What's the area? The total area. The total area is infinite because it's harmonic series in essence. Okay, you're doing 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus etc. up to 1 by infinity. And harmonic series is one series that diverges in terms of the power law series, right? So r equal to 1, you don't even have an average. You don't even have a mean if it is a truly infinite distribution. Normally what people will assume is it's a power law distribution over a range. And so beyond that, suddenly it becomes 0. Which is kind of weird, because even though it looks as if it's almost close to 0, so what happens if I make it 0 after this? It's a huge difference. Okay, going from 10 power minus 14 probability to 0 probability is still a huge difference. Because in between 10 power minus 14 and 0 is 10 power minus 15, 10 power minus 16, 10 power minus 300, 10 power minus 750, all these numbers exist. And you're just saying all of them are 0. Okay, just a second. Okay, so this basically, and the other interesting question is, if you have a distribution which is basically 1 by k